Section 3.5 Denial of Wallet. When AI becomes expensive on purpose. Traditional denial of service attacks try to bring a system down. Denial of wallet takes the opposite approach. The system stays up, processes every request, and looks completely normal, while quietly accumulating API charges that can reach tens of thousands of dollars in a single day. This is the billing dimension of OWASP LLM 10, 2025 edition, called unbounded consumption. The risk is fundamentally different from a traditional DOS. The attacker's goal is not to disrupt your service, it is to cause financial damage. Nothing in your application limits how much work it will do or how much that work will cost you. This makes denial of wallet especially dangerous for developers shipping their first AI-powered feature. A chatbot with no rate limiting, no spending cap, and an open endpoint is not just a security risk. It is a financial liability that can generate a catastrophic bill before anyone notices. Let's compare traditional denial of service with denial of wallet. With a DOS attack, the goal is to make the service unavailable. Users see the service is down, you see uptime alerts, and detection is immediate. With denial of wallet, the goal is to drain your billing account. Users see the service working normally. You see nothing until the invoice arrives days or weeks later. A DOS attack uses high request volume to saturate bandwidth, and you defend with content delivery networks and DDoS protection. Denial of wallet uses crafted inputs, stolen API keys, and missing limits, and you defend with rate limiting, token caps, and spending alerts. The most important difference is timing. A successful DOS is immediately obvious. A successful denial of wallet attack may go completely unnoticed until your monthly invoice appears, unless you have spending alerts configured in advance. To understand why denial of wallet works, we need to understand how AI API billing creates the risk. AI providers charge per token, a unit of text that's approximately 4 characters. Both input and output tokens are billed, with output typically costing more. For example, GPT-4o charges about $2.50 per million input tokens and $10 per million output tokens. This pricing model has a critical asymmetry. The cost of a single request can vary enormously depending on how much text is sent in and how much the model generates in reply. A simple one-line question costs almost nothing, but a request that floods the context window with a 50,000-word document and asks for detailed analysis costs orders of magnitude more. An attacker who understands this asymmetry can craft inputs specifically designed to maximize cost per request, without triggering any of your usual alarms. There are 2 primary ways an attacker can drain your AI budget. Attack path 1 is request abuse. The attacker interacts with your AI endpoint directly, crafting long inputs or triggering loops. If your application has no rate limit or token cap, these expensive requests flow straight through to the AI provider, and charges accumulate on your account. Attack path 2 is LLM jacking. Your API key gets exposed in code, logs, or configuration. The attacker calls the AI API directly with your key, bypassing your application entirely. Both paths lead to the same result. Your provider bills you for usage you never authorized, and charges accumulate silently until you check the invoice. Let's look at each path in detail. Attack path 1, request abuse. When your AI endpoint has no rate limiting, no input length validation, and no output token cap, anyone who can reach it can generate arbitrary amounts of billed compute. 3 patterns drive most abuse. First, token flooding. The attacker sends requests designed to fill the model's context window, pasting massive text or requesting detailed analysis of very long documents. A sustained campaign can exhaust a monthly budget in hours. Second, prompt injection triggering loops. Attackers embed hidden instructions that cause the model to enter tool calling loops. Each iteration issues another build API call, and the resulting token usage can far exceed what a normal request produces. Third, mass automated requests. Without rate limiting, a single script can send thousands of API calls per minute. Even if each request is modest, the sheer volume produces ruinous costs, especially for expensive operations like multi-step agentic chains. Let's look at what a vulnerable endpoint looks like in code. This is a simple fast API endpoint that accepts a user message and passes it directly to the AI API. Notice what's missing. There's no check on the length of user message. An attacker can send a 100,000-word input, There's no max tokens parameter. The model generates as long a response as it decides is appropriate. And there's no per-user tracking. One script can exhaust your entire monthly budget. The impact is severe. A single crafted request with a very long input and no output cap can cost hundreds of times more than a normal interaction. An automated script can exhaust a monthly AI budget within minutes, and there is no service disruption to alert on. The system keeps working normally while charges accumulate silently in the background. Here's the secure version with layered defenses. Step 1. Validate input length. Before sending anything to the AI, check that the message doesn't exceed 4,000 characters. If it does, reject with a 400 error. This prevents token flooding. Step 2. Check the daily budget. Track cumulative token usage per user per day using Redis. If this user has consumed their 50,000 token limit, return a 429 error. Step 3. Cap output tokens. Set max tokens to 1,000 on every API call. This is the single most effective control. The response cannot exceed this limit. Step 4. Record actual usage. After the call, record input and output tokens against the user's budget. Each layer catches what the previous one misses. Input validation doesn't limit output. Output caps don't constrain input. Per-user budgets don't prevent a single expensive request. They prevent sustained abuse over time. Attack Path 2. LLM jacking. This refers to attackers using stolen API keys to call AI provider APIs at your expense, a term coined by Sysdig's threat research team in 2024. It works because AI API keys are bearer tokens. Anyone who has the key can make calls charged to the owner's account. There is no second factor of authentication. How do keys get stolen? An API key in a public GitHub repository, committed inside a Docker image, captured in logs, or embedded in a JavaScript bundle can be found by automated scanners running continuously. Stolen keys are typically exploited within minutes of being published. The cost is not theoretical. A compromised Anthropic key was documented generating $46,000 in charges per day. A stolen Gemini key accumulated $82,000 within 48 hours. A stolen key may sell for $30, while generating damage thousands of times that amount. Let's look at exposed versus secure API key management in code. In the vulnerable version, the API key is hard-coded directly in the source file. When committed to a repository, the key becomes part of Git history permanently. Even if you delete the file later, the key remains in every clone. Automated scanners will find it. In the secure version, the API key is loaded from an environment variable. The .env file is excluded from Git. The SDK throws at startup if the variable is missing. Fail fast, not silently. But secure storage alone isn't enough. You also need a hard monthly spending cap on your provider dashboard as a last line of defense. Configure a billing alert at 50% of expected spend. Scan for leaked secrets before every Git push. And if you suspect exposure, rotate the key immediately. Why is standard rate limiting not enough for AI endpoints? Standard rate limiting was designed for APIs where requests have roughly uniform cost. AI APIs break this assumption entirely. A rate limiter allowing 60 requests per minute provides no protection against a single request consuming 100,000 tokens. A burst limit prevents rapid-fire attacks, but does nothing about a slow campaign sending maximum-length inputs. You need multiple strategies. Request rate limiting handles floods but misses expensive single requests. Input validation handles token flooding but doesn't limit output. A max tokens cap handles runaway responses but doesn't constrain input. Per-user budgets handle sustained abuse but are bypassed by distributed attacks. Spending alerts catch both paths but fire after charges occur. Hard caps stop costs but may interrupt legitimate users. No single control covers every scenario. You need the combination. Let's map each attack vector to its defenses. For token flooding, validate input length and reject oversized inputs. Set max tokens on every API call to cap output. For prompt injection triggering loops, limit tool calling iterations and cap total tokens per session. Apply input scanning for injection patterns. For mass automated requests, apply per-user and per-IP rate limiting at the gateway level. Add bot detection for public-facing features. For leaked API keys, set a hard spending cap and billing alert at 50% of expected spend. Rotate keys regularly and scan Git history before every push. For lack of spending visibility, configure billing alerts before deployment. Track per user token cost in your application metrics. The critical insight: application level controls protect against request abuse, and provider level controls protect against LLM jacking. You need both. Provider side spending controls are your last line of defense. They cap the damage even if an attacker bypasses every application level control because they act directly on the API key at the provider's infrastructure. For OpenAI, set monthly spend limits under billing, then limits. Configure a notification threshold and a hard limit that blocks all calls once reached. For Anthropic, configure usage limits under settings, then limits. Set both an alert threshold and a hard cap. For Google Cloud, use budget alerts under billing for notifications and apply API quotas to cap requests per minute and per day. The rule that matters most: configure spending controls before you deploy, not after the first unexpected bill. A billing alert set up the day after an incident has already failed at its only job. Remember, every AI endpoint is a cost center. Rate limiting, token caps, and spending alerts are not advanced security measures. They are the minimum viable deployment configuration for any public-facing AI feature. In the next section, Section 3.6, we'll look at how attackers corrupt the knowledge base your AI reads from through vector and embedding weaknesses. For more details, visit wisebuilder.dev.